we've looked at average rate of change, we've looked at instantaneous rate of change, and now we're going to look at how to work out the instantaneous rate of change at any point along the curve. Okay, we know that we can have 2 points on a curve, point P and point Q, all right, and then we can find the average rate of change, which would be the gradient of from point P to point Q. We can find the gradient of that secant, but we can also, what we can do is we can take the limit as h approaches 0, and we can move this point Q all the way down so it's basically on top of point P, and we can find the instantaneous rate of change, which is the gradient of the tangent at P. Okay, then the way we can do this, we've done this last lesson, we'll set it up again, is we can find the gradient PQ, alright, and we're going to take the limit as h approaches 0. So that's going to be average rate of change first, f of b minus f of a divided by b minus a. Okay, that's our average rate of change function. I'm going to find the gradient of the secant first. Now, B is point B, that's our second point. Okay, so that's point Q, and now that is our x value is x plus h, and our y value is our function value at the point x plus h. So f of b is f of x plus h minus f of a is f of x, that's from our first point P, f of x, and that's divided by b minus a. Now b is our x value of q, which is x plus h, and then a is our x value of p, so that's minus x. And what you can see here is on the bottom of our fraction, the denominator, we've got x and minus x. Now those two will just be 0. So we can simplify this and find our gradient PQ equals f of x plus h minus f of x, and that's all divided by h. And that's our average rate of change, okay, between 2 points. Now to find our instantaneous rate of change, okay, that would be the limit as h approaches 0 of f of x plus h minus f of x divided by h. And then when we actually put a curve into this function, h's on the top and bottom will cancel out, they'll divide by each other, and we'll be left with some value or some expression. Okay, so we found the gradient of our secant, we found our instantaneous rate of change, which is also the gradient of the tangent at point P. What we can do now is when we take the limit, don't forget that we are seeing as Q moves closer and closer to P, so that's on top of P. We get that tangent. Okay, the next thing we need to do now is have a look at an example. Okay. Oh, actually, before we get to the example, we can formalize this rule. Okay, this is the instantaneous rate of change, and we use f dash of x. Okay, f prime of x. Okay, and that stands for the limit as h approaches 0 of f of x plus h minus f of x all divided by h. That's our derivative. Okay, and this formula is called differentiation using first principles. The way we remember it is that it's the first way we learn how to derive a function, and we'll find the derivative of a function. It's basically useless after the first 2 weeks or week, and we don't ever see it again. But it's something that you will be tested on, and it's in your syllabus, so we need to have a look at it. Okay, so that's our derivative formula. Okay, differentiation by first principles. We can also use dy dx instead of f dash of x. This is called the Leibniz notation. It's when we first started doing differentiation in Europe. It just says, you can think of it as derivative of y and then with respect to x. Y is your function and x is the variable inside your function. Or you can use f dash of x or f prime of x. Doesn't matter. Alright, let's say we've got a function. Function of x is equal to x squared plus 2x. right? And we want to find the derivative of this function using first principles. First thing we would do, is set up our formula. F dash of x equals f of x plus h minus f of x, all divided by h. Oh, not quite. That's not our formula. Let's move that across. We've forgotten to put in our limit as h approaches 0. Okay, so this is our formula for our derivative. The best way to approach a question like this is to work out your numerator first, this top part of your function, because it's going to get annoying to rewrite all of this stuff every single time you simplify what's going on up here. You'll see what I mean in a second. Okay, so what we're going to do is we're going to simplify, or we're going to find out what our numerator is first before we plug it into this formula. So I'm going to write f of x plus h minus f of x is equal to. Okay, now this is function notation. We've done this a few times. We can see our original function is x squared plus 2x. That's f of x. But we want f of x plus h. Okay, f of x plus h. So wherever we see an x in our original function, we're going to replace that with x plus h. So we're going to have x plus h squared plus 2 times x plus h minus f of x. So minus our original function, x squared plus 2x. Now our brackets are important here because this minus out the front acts on everything that's inside the brackets. Now let's expand and simplify here. We're going to have x squared plus 2xh plus h squared plus 2x plus 2h minus x squared minus 2x. That's not a plus 2x there. Alright, now we can take a step back. It's a long expression, but we can cancel out some of these terms. We've got a positive x squared and a negative x squared. That's just going to be 0. And we've got a positive 2x and a negative 2x. Again, that's just going to be 0 when you collect like terms. So we can say our numerator now is equal to 2xh plus h squared plus 2h. Okay, now one more step before we go back to our gradient function, okay, is to factorize by h, because this is going to make it really easy when we go to divide by h. What we're going to do now is put h outside of the brackets and factorize by h. So everything that's being multiplied h, we basically take an h outside the brackets like so. So if you expand in your head, you can see that that is the same as what's written above. 2x times h, then you've got h times h is h squared, and 2 times h is 2h. So we've just factorized an h there. Alright, so that is the numerator of our derivative. Let's go back to our derivative now. F dash of x equals the limit when h approaches 0. Oh, we can write our numerator in now. H multiplied by 2x plus h plus 2, and that's divided by h. And you can see now why I factorized. It makes it a lot simpler now. We can just divide the top and bottom by h. Simple. And so that leaves us with the limit. And yes, you have to write this each time. The limit as h approaches 0 of 2x plus h plus 2. And then from here we can simply sub in h equals 0 into that expression, and we find that our derivative, we can say therefore our derivative equals 2x plus 2. Alright, so that is the derivative of f of x equals x squared plus 2x. We can say that is the derivative of x squared plus 2x. Okay. A lot of stuff there. We're going to try with one more example before we go into some questions. Alright. Let's say that we're going to use y this time. Y equals, let's say it's 2x squared plus 5x minus 2. Alright, so we've got another quadratic, but it's a little bit more complicated. We've got this constant term at the end, but you'll see it's all going to work out. I'm going to use Leibniz notation now as well, just for a bit of practice. We can say dy dx, so that's the derivative of y with respect to x, equals our limit expression. So the limit when h approaches 0 of f of x plus h minus f of x, all divided by h. Okay, same again. I'm going to do my numerator first. I'm going to say f of x plus h minus f of x is equal to, now wherever I see x again, I've got to replace it with x plus h. So it's 2 outside of x plus h squared plus 5 outside of x plus h minus 2. And then I'm going to take away my original function. I'm going to do this all in brackets so I don't get my negatives mixed up. Plus 5x minus 2. Alright, next step, expand and simplify. So this is 2 outside the brackets of x squared plus 2xh plus h squared plus 5x plus 5h minus 2. Then I've got a minus 2x squared minus 5x, and then I've got a plus 2. One more line, I'm going to expand these brackets now. We're going to have a 2x squared plus 4xh plus 2h squared. Then I'm just going to copy and paste the rest of it because that doesn't change. Like so. Okay, now just like before, we can cancel out some of these terms. They're going to equate to 0. So we've got a 2x squared and a negative 2x squared. That's going to disappear. We've got a positive 5x and a negative 5x. We've got a negative 2 and a positive 2. And that looks like it. So we can say that our numerator is equal to 4xh plus 2h squared plus 5h. Cool, and last step, we're going to factorize out this h. Just to make it simpler for the next step, we can say that h outside, so we've got to take away an h from everything, well, sorry, divide an h of everything. It's 4x plus 2h plus 5. Okay, now let's go back to our derivative. dy dx equals the limit when h approaches 0 of our numerator of h 4x plus 2h plus 5 divided by h. Okay, and we can now divide the top and bottom of this fraction by h. They will equal out. And then we can write that equals the limit when h approaches 0 of 4x plus 2h plus 5. Okay, now we substitute h equals 0 into that expression because we want to see what happens when h gets really small, gets so close to 0 that it actually is 0. So we treat it like 0, the 2h will disappear, and we're just left with our derivative of y with respect to x is 4x plus 5. There you have it. That's differentiations using first principles or by first principles. Okay, check for the questions now, and I'll see you next lesson.